In this video, we're going to start chapter 3. And the first part of chapter 3 is on light energy or electromagnetic radiation. Before we jump into that specific form of energy, I do want to just define energy and talk real quickly in general about it. So our definition, the capacity to do work or supply heat, which I've never really found to be a super useful definition from a chemistry perspective. We do have an entire chapter on thermochemistry, so we'll talk quite a bit about the heat perspective. We'll talk a little bit about work in that chapter. Most of the work that we do in chemistry tends to be expansion work. If you take a physics class, you'll spend quite a bit of time in your first physics semester on work. For now, I'm just going to define it and kind of leave it there, and we'll come back to that throughout the semester. I do have two main types of energy, so we can subdivide it. Our first one being kinetic energy. And then I am going to put a definition underneath there, so leave a little bit of space. And then potential energy. So kinetic energy is defined as energy in motion. Essentially, it's energy that you're using for something. Potential energy is literally that. It has the potential to actually be used for something. It is stored energy. In chemical systems, it's stored as chemical bonds, so chemical energy. Is potential energy. And it's stored in chemical bonds. The example that makes the most sense to me when thinking about these two and kind of how energy is stored in chemical bonds is if you have a gas grill. So you have a propane tank, right? And in that tank you have propane, right? And it's not currently doing anything. You're not combusting it. You're not cooking hamburgers or whatever it is you're cooking. It's just sitting there, but it has the potential to supply heat to cook your dinner. So in the chemical bonds, I'm drawing propane here. Propane has 3 carbons bonded to each other, and then each of those carbons has a hydrogen. And each of these lines I'm drawing is representing a chemical bond, right? The connections between atoms in our compound. So this is propane. When it's sitting in your tank, each of those lines, right, each of those chemical bonds is storing energy. We then undergo a combustion reaction. I'm not balancing this, so I'm just adding oxygen. We end up breaking those bonds. I get carbon dioxide plus water. So instead of having carbons bonded to each other anymore, I don't, right? And again, this isn't balanced. So if you've balanced reactions before, if you notice, I'm missing carbons, right? The other part, and the part I really want to focus on, is we also are supplying heat. So what we're doing is we're going from potential energy, right, stored energy in the chemical bonds, to heat that you can use to then cook your dinner. Right? So we had the potential when it was sitting there. We undergo a combustion reaction and we convert it to kinetic energy, energy we can use for something. The law of energy conservation is just as it sounds, right? Remember we had the law of mass conservation that told us that mass was conserved. The law of energy conservation tells us that energy is conserved. This is also reworded a little bit, the first law of thermodynamics. And it tells us that total energy remains constant. So during a chemical reaction, my combustion reaction up above, I'm not creating energy or destroying energy, but what I'm doing is I'm converting it from one form to the other. So I'm going from stored energy, my chemical energy, to heat energy, thermal energy. I'm not creating heat energy from nowhere. I'm not taking chemical energy and destroying it. I'm converting one form to another form. So if something loses energy, then something else needs to gain it. So total energy remains constant. That's our first law of thermodynamics. but we can convert it from one form to the other. We can also transfer it from one thing to the other. So energy can be transferred or converted from one form to another, but is not created or destroyed in a chemical reaction. So again, in my example up there, I just transformed it, right, from one form to the other. I went from chemical energy to heat energy, thermal energy, right? That heat energy didn't just, like I said, appear from nowhere. We transformed it into heat energy from chemical energy. So total energy is conserved. Our SI unit for energy is a joule. Because you don't need the one there. You can have more than one joule. Our SI unit is a joule, abbreviated a capital J. Often we talk about kilojoules, so 1,000 joules in a kilojoule. A joule is a derived unit. Remember our 7 fundamental units, a joule was not one of them. And if I was to break it down into its parts, it's a kilogram, so that was our SI unit for mass, multiplied by a meter squared. Meter was our SI unit for distance, divided by second squared, our SI unit for time. So if we were to break it down, a kilogram meter squared per second squared is what a joule is equal to. So light energy, I said that's what we wanted to focus on in the first part of this chapter. So light energy is just one form of energy. And oftentimes we'll call it radiant energy. Also called electromagnetic, abbreviated EM, radiation. And light energy is moving, right? It does travel, things aren't stationary, and it often travels in the form of a wave. So we could say that light energy or electromagnetic radiation has wave-like properties. So electromagnetic radiation has wave-like properties. So instead of traveling just in a straight line, we're saying it's kind of oscillating, right, as it travels. I'm going to draw a better picture of that. I just wanted to make sure everyone was on board when I say a wave, kind of what I'm talking about. So our wave is going to be characterized by 3 things. One, our wavelength, our frequency, and then our amplitude. So I am going to sketch a picture of a wave here, and I might have to do it a couple times because I do want it to be somewhat symmetrical. So this dotted line I made is my center line, and as I go up and down, the distance between the center line and the top of that wave should be the same as the distance between the center line and the bottom of that wave. And mine isn't really great. Let's actually give that another shot because I want it to be pretty accurate. So I'm going to go up and then I'm going to come down, and I want those distances to be somewhat equal. It's a little bit better. So wavelength is the distance between 2 consecutive peaks or 2 consecutive troughs, which is the bottom, right? It's the peak turned upside down. So those are my wavelengths. Our symbol for wavelength is the Greek letter lambda. So this is my wavelength. And that's our distance between 2 consecutive waves. Peaks. Sorry guys, 2 consecutive peaks. Or troughs. And again, they should be the same. Our wave isn't collapsing as we go, it's not getting bigger. So the wavelength is going to be the same. If I was to draw another one on here, the distance between here and here should be the same as this one. Again, I am not a great artist, so please look at pictures. I'm going to erase this second part that I added because those distances should be the same, and I don't want you to have to look at it with it not being the same. So wavelength, the distance between 2 consecutive peaks or troughs. Again, that is remaining constant for a particular wave. Not all forms of light energy have the same wavelength, but the wavelength for a particular form or a particular, stream of energy isn't changing. So I could draw another wave that has a much smaller wavelength, right? So my wavelength for this one is much smaller. So my wavelength. Amplitude, we're not going to use much. I am going to add it on here, but I'm not going to really talk about it. So amplitude is the height from the peak to this midline or the trough. And again, it should be the same. So this is my amplitude. We're not, like I said, we're not going to really use it. I'm just adding it so that way it's complete. The other part that we are going to use quite a bit is frequency. And frequency is, I can't really draw it on there, but we can describe it. So my definition for frequency, and my symbol is going to be the Greek letter nu. Be really careful that's not a V. It starts out like a V on one side on the left, but then it kind of curves on the right side, right? This is a V, this is nu. In this chapter, we are going to have equations that have nu in it. We are also going to have equations that have V for velocity in it, so be really careful to keep your V's and your nu's straight. So frequency, this is the number of peaks that pass by a fixed point per unit time. And that time can really be anything. It's generally defined as per second, but it doesn't have to be. It could be per hour, just whatever, some unit of time that you want. All light travels at the same speed. What speed does light travel at? It's kind of a trick question. The speed of light, good. Light travels at the speed of light, which is why it's called the speed of light. So these waves are traveling, both of them. I have 2 waves here, wave A and wave B. And they're traveling at exactly the same speed, right? The speed of light. The one on top, wave A, has a bigger wavelength. The one on the bottom has the smaller wavelength. So if I was to have a fixed point, right? Let's say that this is my point right here. And these guys are traveling at the same speed. Which one is going to have the larger frequency, right? Which one, this should be straight for comparison, which one is going to have more peaks passing by this fixed point per unit time? Yeah, good, the one with the smaller wavelength, right? Because they're closer together. So the smaller the wavelength, the larger the frequency, right? If those waves are spread further out, then less of them will pass by that fixed point. So wavelength and frequency are inversely related. So frequency and wavelength and frequency are inversely related, right? As our wavelength gets smaller, our frequency goes up. As our wavelength gets bigger, our frequency goes down. So larger wavelength equals smaller frequency. Smaller wavelength equals larger frequency, right? Frequency, the number of peaks passing by that fixed point. Mathematically, the relationship between the two is if I was to multiply my wavelength by my frequency, I actually get the speed of light. C is the speed of light. This equation is on the back of your periodic table, so you don't need to memorize it, as is the speed of light. So you don't need to know this. We will use it in this chapter though. So C is my speed of light, which is also on the back of your periodic table. So 2.998 times 10 to the 8th meters per second. So that's how fast both of those waves would be traveling. And again, lambda is my wavelength. And we already did speed of light. Nu is my frequency. We can do an example problem. We want to know what is the wavelength. Let's do it in nanometers of a wave if its frequency is 1.85 times 10 to the 15th seconds to the -1, so per second, right? Seconds to the -1 is the same thing as 1 over a second, right? Just algebra, x to the -1 is equal to 1 over x. Switch x with anything you want, hertz, butterflies, seconds. If you have something to the -1, it's 1 over it, right? It's the inverse. Sometimes I'll write the units with the -1, sometimes I'll write it as 1 over, so just do watch out for that. It's not that I'm trying to trick you, it's just the same thing in my head. So sometimes one comes out and sometimes the other comes out because I know they're the same, so it doesn't matter. So our problem, what is the wavelength in nanometers? So we're solving for lambda, right? That's our unknown. And we do want it in nanometers. So we are gonna have to do a unit conversion. I know my frequency is 1.85 times 10 to the 15th per second. And then I know that the relationship between these two is that if I was to multiply them, they're equal to the speed of light. Speed of light is constant, 2.998. Again, that's going to be provided. It's on the back of your periodic table, so you don't need to memorize it. And then meters per second. So essentially, you just have to watch out for units. Because my frequency is given to us in terms of per second, I don't have to do anything with that. If it was given to us as hours to the -1 or weeks to the -1, I would have to convert it to per second because of my units on the speed of light. I guess alternatively, you could convert your units on the speed of light to match your frequency. I generally just leave the constant alone and then convert frequency, but you could do it either way. They just have to match. When I plug them into this equation to solve for wavelength, it is going to come out in meters, again, because my units on the speed of light are meters per second, but then we'll just do a unit conversion when we're done. So I'm essentially just plugging things into that equation. I'm going to rearrange first. If you want to plug it in and then rearrange, it doesn't matter, but I'm going to take this equation that I just erased the box around, and I'm going to solve it for wavelength because that's my unknown in this problem, right? So if I divide both sides by frequency, I get my wavelength. And then I can just plug everything in. Oop, forgot the 8. 2.998 times 10 to the 8th meters per second divided by my frequency. And then my per seconds are going to cancel. I'm going to be left with meters, so we'll write that over here, and then we'll do our conversion. So I'm grabbing my calculator. Make sure you're using that scientific notation button on your calculator. If you're not, then make sure you put parentheses around your numbers before you divide them. And I end up with a wavelength of 1.62 times 10 to the -7th meters. Again, we're not done because our problem wants it in nanometers, but now it's just a unit conversion. So how many nanometers in a meter? This is one of the ones that you needed to learn. Yeah, good if you got 10 to the 9th. We haven't used it much since we learned it. We'll use it in this chapter a fair amount. But there's 10 to the 9th nanometers in 1 meter. A nanometer was one of the units that's smaller than the base unit. So on the table that you were given originally, it would have said that there's 10 to the -9 meters in 1 nanometer. But I like to think of them as positive exponents. So lots of the smaller one, which is nanometers in that meter. So just be careful not to convert it upside down. And then we can just do dimensional analysis. 1.62 times 10 to the -7th meters. Since meters are on top, the 1 meter is going to go on the bottom, and then the 10 to the 9th nanometers is going to go on the top. So grabbing our calculator or just moving the decimal place over, whichever, since it's in scientific notation, this one's probably easier to just, it's easy to do it in your head. We get 162 nanometers. So really it's pretty straightforward because you're given the equation, right? You're given this. You're also given the speed of light. So it's really just a matter of plugging things into that equation, doing the math, and then the unit conversion after is probably the trickiest part where people goof up. Either that or not using the scientific notation button on their calculator. So as we said, not all light energy has the same wavelength, so it's not all going to have the same frequency. We are going to add energy into this in a little bit. But if we were to take all of our electromagnetic radiation, right, all of the forms of light energy, and then order them in order of wavelength or frequency or energy, we end up with the electromagnetic spectrum. So electromagnetic, again, EM, spectrum. So this is the continuous range of wavelengths and frequencies and I am going to add energy of all forms of radiant energy or light energy. Again, radiant energy is just light energy. So essentially, if we were to take all the forms of light energy and we were to put them in order of wavelength, frequency, or energy, we get our electromagnetic spectrum. And different again, maybe subsets within that spectrum are given different names depending on what the wavelength is. And I don't really care so much that you know the actual numbers, but I do want us to know the order. So at one end, and again, I do want you to know the order here. So I'm going to have gamma rays at one end. And they're going to be my highest energy, my highest frequency, and my longest wavelength. Sorry, my shortest wavelength, right? Remember, wavelength and frequency are inverted. So gamma rays. I will add those arrows after we do the different types. After gamma rays, I'm going to have X-rays, ultraviolet, so UV, right, our sun, which also gives off other rays, but the ones that, cause damage. Visible, the only ones that we actually see. So when we see colors, we're seeing in the visible spectrum, right, of our electromagnetic spectrum. The visible spectrum is about 400 to 700 nanometers for the wavelength. Infrared, so IR, you have those night vision glasses. Microwaves, yes, microwaves run on microwaves. And then radio waves, kind of running out of room here, radio waves. So gamma rays at one end, radio waves at the other. As we go from left to right, my wavelengths are getting larger. So larger wavelengths on this side. Remember that wavelength and frequency are inversely related. So if I have larger wavelengths, I'm going to have smaller frequency. And we haven't added energy in yet, but I'm going to add it here just so it's complete. So larger wavelength, smaller frequency, and actually smaller energy, so less energy. Energy and frequency are going to be directly related. If I go to the other end, these are going to have smaller wavelengths. So these are going to have larger frequency or higher frequency. And then they're going to have higher energy or more energy. Gamma rays being the most energetic of all forms of electromagnetic radiation. So again, I do want you to know the order. So I could give you a question that said, radio waves have a larger or smaller frequency than ultraviolet rays, and you would have to tell me if it's larger or smaller, that sort of thing. So do know this order. Without looking it up, because that would be cheating on tests and quizzes, I do expect you to be able to just answer these without paging through your note. I had said visible was about 400, and you don't have to memorize this, to 700 nanometers. So different colors have different wavelengths, different frequencies, and different energies. But again, we're only seeing things in the visible range. Some animals can see ultraviolet or infrared. We cannot, however. We only see visible, which is why it's called visible. Red is at this end, and then violet is at the other.